morning.
Good morning.
I'm putting my phone here with the timeline since Frank's not here with us. They're counting down, so I'll try not to be too abusive to you. As Tim said, he had contacted me probably a couple months ago and asked if I would be interested in doing a seminar on safe bending boiler tubes. And I thought, sure. And then after about 3 seconds, I thought, well, that'll last 5 minutes. I probably had to come up with something else to talk about. So the title's evolved several times, and it's now welding versus riveting in locomotive boilers. And I want to talk about riveting a little bit because it's important to understand the background of why the railroads, the builders, and the railroads started eventually going to welding in very many facets of locomotive boiler use. So, a little bit of background on the riveted stuff. Riveted construction had been around for many, many years. It was used to attach metals to themselves, whether it be cast iron, steel, even other types of materials, copper, all that kind of thing. But in what we're going to talk about is going to be called hot riveting, where you're not using pop rivets. You're using rivets that are in locomotive construction. Typically, they ranged in size in the shank from about 3/4 of an inch. I'm sorry, yeah, well, 5/8 in the occasional uses, but basically 3/4 of an inch up to about 1.25 inch shank. And their length could vary from maybe just 3 inches long to up to 10 inches long. And the longer the rivet, the more difficult it is to drive the rivet. When you're actually, the one end is already formed, of course, and you buck that end. The other end, you have to put a rivet gun, or depending on if you got some really fancy equipment like a bull riveter, like that at Roanoke, otherwise you'd have to have another guy who knows what they're doing. You just don't put it on and drive it, because what happens is the rivet, since it's so long, depending how much of a grip, which is the distance between face to face of what you're riveting together, the rivet's going to want to bend as well. It's really hot, soft, and you have to counter that constantly when you're riveting by hand. So anyway, riveting used for many, many years. It still is in certain cases, not so much the hot riveting, but you use it for, nowadays, for restoration of locomotives. It was very widely used for bridges. Everybody seen bridges with rivets on them, and a lot of these bridges are very old and they're riveted and they're still really good shape. They were used for, of course, pressure vessels and tanks like that. Buildings, Empire State Buildings riveted together, just as a skin on the outside. So riveting was very common, very proven, and very reliable. Those are the positives. The drawbacks is it's fairly labor intensive, well, it's quite labor intensive, and you need all kinds of stuff mechanically to back it up. But typically a riveting crew would consist of 2 guys riveting, one driving the rivet, the other one bucking the rivet. So the rivet's put in the hole, and there's a guy has to be there with another rivet gun or a bucker, or again, if you have a bull riveter, have to be handy in your closet, you use that. You also need a heater. A guy on a forge heats the rivets. You're looking probably in the temperature range of a little over 2,000 degrees. They should be just shy of sparking. When you get a rivet really hot, a piece of metal really hot, you get it too hot, it starts to spark. And what that is, the spark stuff is the carbon starting to burn out of it. Don't want to go quite that hot. Then you had 1 or 2 rivet handlers, maybe seen, other than the Three Stooges thing, how we handle rivets. You have basically a guy would take the rivets out from the heater, from the forge, and they either put it right in a hole, or you had to hand it off to somebody else. If somebody else is inside of a boiler, you're not going to be just trying to throw it up through the manhole cover. So you can have a minimum of 5 people typically on a riveting job. Then you also have to have a forge, you have to have the fuel hooked up to it to get the forge going, heat things up. So then you need the tools. You need at least 1 rivet gun, probably 2. You need to have chipping hammer. Once the riveting job is done, a chipping hammer is like a small rivet gun that has a tool on the end of it. It's curved for rivets. You have what's called caulking, and again, caulking, you don't go to the True Value store and caulk your boiler. Caulking is, you have a joint, and these things are beveled for a reason. This is a side view of this particular rivet configuration. You actually drive this piece right here on each end, and that forces the metal from this onto the metal from that. When you just rivet a joint, it's going to be very tight, but it's not going to be waterproof or steam proof. You have to drive that metal from the one piece into the other, and that's what makes your seal. So you have to caulk with a blunt tool to do that, and plus, as the rivets are put in, they go away. Thank you. These are just showing holes, but you have a rivet head here. Sometimes you have a little excess material, and you have to trim that off. And what that does, it also seals the rivet to the face of the piece as well, so it won't leak. So you have all that labor to do and the tool to do. And one other thing we got to talk about here, and we'll go back to this a little bit later. When you do riveting, you have to take into account that you're going to weaken the metal. You weaken the metal because you're putting a bunch of holes in it. And what you have to calculate, you have to think about is the efficiency. Here we go. A solid plate is 100% efficient. You've not put any holes in it, you've not weakened it. When you put holes in it, you're going to weaken it, especially in a row, in a line. So what you have to do, it's a very simple way to put this is, if you have a 4-inch pitch, I'm not using a pointer, I'm just using this. A pitch is from center to center of each hole. So let's just say that's 4 inches. You put rivet in there, rivet holes in there, that say just for discussion purposes are 1-inch diameter. So basically you go from here to here, so you have 1/2 and 1/2, that equals 1 rivet hole. So if it's 1-inch rivets, you have a 4-inch pitch. What you do is you take your 4-inch pitch, you subtract 1 inch for the diameter of the hole, and you divide it by the pitch again. And in this case, a setup like that with 1-inch holes 4 inches apart, that plate is 75% efficient versus 100% because you put these holes in here. That making sense?
So it's directly proportional? Like it's not, you know, you put one hole in and you weaken it more than just what it seems like it would? Like you said 25, if you take a 1 inch out of 4 inches, it's 25% weakened. I guess I would have thought it's 33 or 50 or
No, that's basically how it is. Now again, that's very simple terms because there's all kinds of configurations, and that's why you have, and this is only a few. Now, I'm going to go back to the efficiency in a little bit here, because the first thing we're going to talk about, efficiency doesn't matter in this particular case, but we'll go back to that in a minute. But yeah, that's a very basic way to say that. Now, I'm going to see if I can use this properly. That way. Can you advance the one?
Oh, yeah, no, it should. Okay, hang on.
There we go. Now, this is an illustration of a single riveted. There's only one. This is looking at the end. There's one row of rivets here, and then this is a flange, and then the other piece joins it. You have a hole through here, and you drive the rivet. There are issues with this kind of a joint, especially inside of a firebox. Let's just say this is the front tube sheet. Tubes are in here. It's flanged, and then it meets up with the crown sheet. What you have here is a lap. So the fire's on this side, get a lot of heat on this piece right here, and it can't hardly transfer its heat very well to the water on the other side. So the rivet itself, and this piece from about here to here, gets much hotter than all the adjacent material. That's one of the problems with riveting. And the heads of the rivets, again, it's going to get hot over time. It's going to burn the carbon out because fireboxes, it's kind of warm in there, 2,000 degrees plus sometimes. On the water side, corrosion. Water, after a while, is going to start corroding the heads of the rivets. So, in the firebox, this will last you quite a while, but The N&W, as Tim mentioned, was the first railroad to weld fireboxes. And this is it's just the inside of the boiler shell itself. I'm going to go back to that again too. Now, welding,
It should work. I'll give it a
oh,
shot.
should work now? Hey, now look at that. All right, this, maybe you've probably seen this before. This is actually number 1200, the first A. This is the firebox, and this is the combustion chamber, and this whole thing goes inside the shell. As you can see, it's set up for welding. You can see the weld seam here. There are no riveted anything in that firebox. It eliminates all these issues we talked about. You're not going to have seams leaking. You're not going to have rivets leaking or burning up. Takes care of a lot. There's no more lapping. There's no problem there. And for labor, you need two guys, a welder and a helper. And the helper typically has the crappy job. He has to follow up the welder, chip all the slag off, and also usually with a grinding wheel, grind off any imperfections or if there's any gaps or anything like that. He has to grind that out so then the welder comes back and does another pass. You're going to have several passes with the weld to make the sheet, at least as a minimum, as thick as itself or slightly thicker at all the weld joints. Another advantage is, again, no joints that can leak when you're done, no hot spots, and it's easier to fit up the plates to each other. Versus what we had before with that lap joint. You have to flange it, of course, but you don't have to worry about the lap and fitting that all. You can't have a gap in the joint. You have to have it nice and tight, and it takes time. You have to heat it up, pound it some more, get it fit nice. And you have to get your holes. The holes are already in the plate, but then you have to run a reamer through before you put the rivets in. That all goes away. Now, drawbacks back in the 30s. Again, N&W did this in 1936, and that was their standard practice from there on out with N&W at Roanoke shops. No more riveted fireboxes. But at the time, welding was very specialized. A lot of skill. The welding equipment we have nowadays makes things a lot easier than they were back then. But at the time, it wasn't widely used. The more stress it creates. Includes the weld metal and the adjacent material you're welding on. And you have to worry about carbon content in the steel. If it's too low, the material will be too weak as it tends to crack. If the carbon content's too high, you're going to have a very similar issue. It's going to want to crack, especially because of the quick cooling of the weld metal. Then heat treatment, what's called post-weld heat treatment. After you weld something, depending on what the material is and what the application is, you want to do a post-weld heat treatment. In other words, you're going to put the whole thing in a furnace, heat it up to roughly 1,500 degrees at a minimum of 1 hour. The typical rule of thumb is for each inch of material thickness, you want 1 hour. So if it's 3 inches thick, it's in there for 3 hours at 1,500 degrees. You ramp it up slowly, you hold it for the time you need to hold it to, and you ramp it down. This relaxes everything. All the welds and heat affected zones, they go away because everything is cooled down slowly. When you put weld metal in, if you've ever seen it, it goes from white hot to dark fairly quickly. So it's freezing very quickly, which creates stress on it before you even put a boiler, have pressure on the boiler. Welding eventually became the preferred practice after they figured a lot of these difficulties out. Now we take it for granted, but it's like anything else. Live and learn. You learn the hard way, and many times it's not very pleasant. Now, welding boilers, we're talking about fireboxes right now. We'll talk a little bit later about the barrel. That was another thing. Now, as we said before, the D&H and the N&W were the first users of welding on boilers. The D&H was actually the first, along with Alco, building an all-welded boiler, the firebox and the barrel, the whole shell, everything was welded. In 1937, it was an experimental, I think it was a 280, experimental engine, and it worked out quite well, but again, there were big restrictions on welding the barrel portion, which we'll talk about in a few minutes. The N&W was the first railroad to successfully safe end boiler tubes in the 20s is what I found, and the first to adopt all welded fireboxes like you see here. 1936. Now, we're going to talk about the tubes, safe ending, that Tim had originally asked me to talk about. When every 4 years under ICC rules, until 1998 when the rule was amended, you were required to take your boiler tubes out a minimum, or excuse me, 4 years maximum for a set of boiler tubes in your locomotive. You could get extensions by the ICC inspector if you brought him in. I want to continue to run this. You had to take 2 tubes out of the boiler at the bottom, not the top, not the middle, at the bottom, because that's where the most corrosion would happen. Everything settles to the bottom. Take these 2 tubes out, and if he deemed they were okay, he'd give you 1 more year of operation on a set of tubes. Of course, you've got to replace the 2 you took out. Now, typically, boiler tubes, they corrode and they don't do so well. The lower the barrel, bottom of the barrel, the quicker those tubes start to deteriorate. The higher you go, they're in better shape. So that's why they make you take them out the bottom. But when it did come time for taking all your tubes out, typically a lot of the tubes on the upper portion of the tube pack were in good condition, as long as they had good water treatment. So what they did was, N&W started this, you take the tube out, and this is a tube from 475, kind of familiar with that chooch, I guess, everybody, and the W280 M class. This was in her boiler for about 8 years. So here's a coating of, compared to a newer tube. See the coating of scale on here, but it's really good shape. You don't see pitting and all kinds of nasty things on it. That's the fire side, of course. That looks pretty good. What the N&W did was, when you take a tube out of a boiler, you have to cut each end out of the tube sheet. It's the front tube sheet and the rear tube sheet. And then you take it out. Many times they had what's called a king hole in the 1 or 2 places in the front tube sheet. You get that tube out first. It's bigger than the rest of the tube holes are. You get that first tube out of there, and then you start cutting tubes. You can pull the ones you're cutting out through the king hole. That's what it was for. Take them out, and you have to cut each end off nice and clean, like this. And then what they did was they added a new section onto the old tube. And what they did then, they forge welded those. You get electric welding, and forge welding is a combination of heat and pressure. So the N&W devised a machine that would do both. It would heat up the end of the new one and the end of the old one. After they cleaned the scale off, they would put these in a big roller all together and let them run around for quite a bit and knock all the scale and crap off of them. And then they prepared both ends, and they would forge weld them. So they put them together, and the machine would heat up right here for about ½ an inch or so, and then at a given point, the machine would put pressure on there and push them together under those high heat and pressure and let it cool, and it would melt themselves together to make a new old tube. That's safe ending. And it saved the railroads a lot of money over the years. And the rule was you may have up to 3 safe ends per tube. I'm not sure where they come up with that, but that's what the ICC rules were. Now, we did 475's overhaul for the first time back in 1991. We took the tubes out, and I was amazed to see there were quite a few tubes that had 4 and 5 safe ends on there. But if the ICC guys are around, hey, you know, you don't get caught. And they worked fine, but 3 was the maximum you were allowed to do by the rules. Let me worry. Anyway.
Was this just because you had weak spots somewhere in the middle of the tube?
It's why you're only allowed to have 3?
3 or more? I mean, it looks to me like you just have them on the front tube sheet and on the back tube sheet. The rest of it would be continuous.
Correct.
Why would they have so many? That bad place?
Well, because what they do, they use it. That's a very good question. You put brand new tubes in, and then after 4 years, you cut them out, cut both ends, of course, and you put a safe end on. They put it back in the boiler again, maybe a different locomotive. Then what they typically would do is sometimes they go, if the tubes are 18 feet long in one class of locomotive, they take them out, clean them up, safe end them, and maybe put them in a little shorter locomotive. But over time, what they would do, they keep cutting off the same end all the time. So what they would do, if a safe end, they would safe end onto the safe end. And so you might get these pieces that might be this long or that long, and they keep just adding on to the one end as they cut the other end off all the time, and that's where you end up with, well, a maximum of 3 supposedly, but N&W kind of cheat a little bit. Make sense?
Yeah, yeah.
So boiler tubes would last, what's an average, decades or years or what?
I've heard of, now this is from regular service to the tourist service. I'll give you an example. Number 972, a Canadian Pacific 10-wheeler, it ran for many, many years. George Hart owned it. Had a tube job on the Canadian Pacific and then ran 3 or 4 years and then it was retired. George bought the engine and he was able to get 27 extensions on that locomotive. So the tubes were good enough because of good water treatment and care that as long as they don't get corroded badly and pitted badly or a lot of scale on them, you can continue to keep it in service. Now that's really unusual, 27 extensions. I mean, 4 or 5 extensions is pretty good, but George is somehow able to keep them in service that way. But typically, 4 years back in the day was a maximum unless you had extensions because they ran the heck out of these things back in the day. It was in the shop, it wasn't making money for the railroad. So they ran the heck out of them, and even if they had good water treatment, depending on how the service they were in, they would actually deteriorate from the inside, the fibers part of it, out because of the constant cinder cutting. It would start making them thin. This tube here is actually a little thinner. These were originally made, maybe you can see it from here, but this is thicker than here. And that's not from the outside, from the water side, that's actually from the inside. The constant, I mean, it's basically constant sandblasting through the tube itself. So again, that's why you look at these things before you go for an extension. You take them out yourself, say, okay, a couple of tubes, oh, that looks pretty good. ICC, ice okay, you got another year. Next year, the same thing. Or you just say, we've had enough of these things depending on what the situation is.
That's why you have the scale on
right?
the side, white scale.
Okay.
Calcium and all that crap around it.
That's why I said I probably had some more stuff this talk because that doesn't take all that long. Okay, now, we're going to talk about welding in stayed areas versus unstayed areas.
Those holes are stable.
I'm going to go here. I went on and got to show this illustration. Now, just for entertainment purposes, I took this photo in 1988. This is the side Pennsylvania Railroad Atlantic number 7002. It was in for an annual. I just wanted to show the tube setup. These are 2-inch tubes, and these are superheater flues. You weren't allowed to safe end the superheater flues on the Type A units. That's what they are. They're 5.5 or 5 3/8 diameter. The superheater flues are right here. You weren't allowed to safe end those, but the smaller tubes you were allowed to do so. But you see how the layout, that's a Type A. Time went on, they went to a Type E, and its tubes, the superheater tubes then were much smaller diameter because on the Type A, the superheater units had 4 passes in them, and the Type E, which is a more modern type, this had 2 passes, so the tubes could be a lot smaller, and you could safe end those. That's a view inside the same boiler, and again, I want this because you can see how they, from the water side, how the tubes are laid out, how they're put in there. So yeah, safe end them maybe. Now Strasbourg, we never safe ended because you can electrically weld them, but it's a bugger to do, and it just wasn't worth it for us. We just take them all out, put all new ones in. Okay, now, welding in stayed versus unstayed. When I say stayed areas, that's a firebox. The firebox is supported by stay bolts and braces. The tube sheets are supported by the tubes. They don't just get the smoke and the products of combustion, as ASME calls it, out to the front end and out the stack. They also serve heat transfer, and they also stay or keep the tube sheets parallel to each other. Again, everything else is braces and or stay bolts. So when you're switching from riveting to welding, it makes no difference as far as your concerns. Stronger or weaker would be rivet or even weld in that particular case because it has secondary support. Keep that part in mind. If you have a welded joint like we saw on 1200's firebox, if one of those joints that were welded starts to leak in a firebox, it's not gonna turn into a catastrophic problem because, again, you have secondary support. Your stay bolts, your braces, it's gonna leak. And it's gonna get your attention. And you're gonna take it out of service and you're gonna fix it. That's why the ICC had no issue with welded fireboxes. They had an issue with welded boiler shells. And we'll talk about that in a few minutes. Okay.
How would you know if it was leaking? Would it be steam going into the firebox, or?
Yes, there'll be steam, and every single time I've been around them, you'll hear it. Unless you're really working the engine hard, you back up, but you're going to hear it's quite audible. And it's like,
When you got a leak?
hello, maybe it's time to take a look at this, but it's not going to catastrophically fail. There's all the other support.
So would you just continue on to wherever you're going, or would you shut things down?
Depends on how bad it is.
Okay.
Because you can have stay bolts leaking, as long as they're not ripping. I've seen already where stay bolts are blowing, so they break at the telltale hole, and you'll have a part in your fire. A big part of your fire was blowing so much water and steam into there, your fire goes out in that particular area. And sometimes if you want to continue on, you might not be able to because you can't make enough steam. So it's like a foolproof thing in a firebox. You're not really going to get in trouble unless you continually go and you have a really bad crack. Well, then you're asking for it. But it gives you plenty of warning to, hey buddy, maybe you ought to take a look in here. Okay.
You write up the condition.
Yes.
And the roundhouse foreman, he looks at it.
And curses
signs
you for doing that, and
turn
then,
roundhouse.
yes, exactly. That's his problem. All right, now, unstayed areas. And again, unstayed areas, there's no other means of support. Unstayed area is something that supports itself. So this is just the smoke box, that doesn't matter. But from here back up to this is a combustion chamber. That's for what it's worth, anybody wants to know. That's an L2, New York Central L2 Mohawk boiler. So there's a combustion chamber up to here. But basically, this port here, the whole way to here, is self-supported. If something happens there, there's no other way to keep it from having a problem. You don't have anything backup on it. Now, what I'd like to do is you think of the tires on your car. The tires are self-supporting. Nothing else is keeping them the shape they're supposed to be. You're looking at what, 30 to 50 PSI typically on a tire, depending what type they are, roughly. But no, there's nothing else holding that air pressure in the tire except the tire itself. Just like a boiler is, locomotive boiler is. And so, if you're running down the road on your car and you're doing some foaming and you happen to run over a railroad spike, you could experience what SpaceX calls a RUD. And for those of you who don't know, RUD stands for the Rapid Unscheduled Disassembly. And you can have one of those on your tire. And I think most of us have had a rapid unscheduled disassembly of their tire in their lives after they're driving. So the issue there is, think about a boiler course, boiler barrel, instead of your tire. If this joint up here, that's a longitudinal joint, riveted joint, keeping this is all one piece the whole way around here, and it's held together there with the rivets. If that joint fails, unlike your firebox, if it fails, it's going to open up. And then you and anybody in the cab will be picked up here, you'll be picked up there, you'll be picked up there. You won't be around to interview for what happened. It will destroy itself and you along with it. So, the Interstate Commerce Commission was very, very fussy about how boilers were constructed.
But that particular part wouldn't be the hottest part.
It would not
as far
be.
as the water. The water as hottest would be over top of the firebox, wouldn't it?
Yes, yes.
Where you'd have a crown sheet fan.
Yeah, this is called the shell. And this courses are called the boiler courses. So the shell, the boiler courses in here and this are only going to get as hot as the water and the steam is. There's no other way to get hotter than that. A firebox, on the other hand, is going to be hotter because it's subjected to fire, to the flame, 2,000-degree heat. And here, you're not going to have that issue, right? This is where's Franco? It's a C&O H8 boiler. He's got somebody around. Now, I'm showing this because you can see, obviously, the firebox, and this is a combustion chamber. These are all flexible stay bolts. And then you're going to see here all the rivets. These are for the circumferential seams to hold the boiler courses together to each other. This is a longitudinal seam, which again, one piece, believe it or not, the whole way around, and they come butt against each other, and they have this seam, and I'll just back up a second real quick. Bear with me. Again, some of the configurations, but looking at it from the side, you can see here's your boiler plate in the middle, and then there's what's called a welt on the inside, and a smaller diameter welt, welt on the outside. And what this is for, this is all part of the efficiency that you were talking before. The efficiency does matter when you have a boiler course you're putting together and attaching. It doesn't matter in a firebox. But again, because there's no other means of support, you have to make sure your efficiency is good enough. And efficiency is put into a form, I'm not going to get on that stuff, but basically, these joints, these longitudinal seam joints, which I showed before, these were typically in the low 80% range, 80 to 83% efficient. So this is what you were stuck with when designing a riveted boiler. You couldn't take 100% because you have a whole bunch of holes in the thing. Now, it wasn't until after World War II, for obvious reasons, that all welded locomotive boilers became available after the American Locomotive Company proved out all welded boiler and promoted them heavily. American Locomotive Company had a furnace big enough to put an entire boiler in the furnace. And they wouldn't do it, of course, when it's in this position. Here you got all these bolts are already applied. You don't want to be putting in a boiler with all the stay bolts in it, and you're going to have rivets down at the mudring here, and a few other places where attaching things. You don't want to do that in a furnace because what makes joints so tight with riveting is, as a white hot rivet cools, it's going to shrink and make the joint very, very tight. Not leak proof, that's what we talked about the caulking at the True Value hardware store. So you put the boiler in the furnace before any riveting was done. Anything else is attached. You just want to relieve, we talked before, stress relieve all the welded joints on a welded boiler. And here we have one of those. This is the D&H engine I talked about earlier. As you can see, there are no rivets on here. No longitudinal seams, no circumferential seams. Again, these are all stay bolts, flexible stay bolts in through here, but there are no rivets. Big advantage of that. Again, they had to figure all this stuff out. So basically, Alco, American Locomotive Company, had this big furnace, and they put the entire boiler assembly in there before any of the other attachments were put on it. Then the whole boiler was relieved. You don't want to have it stressed up even before you put boiler pressure or steam pressure on the thing. You don't want to put it in an already stressed up structure. Now,
is that one of the 280s that had such real high boiler pressure?
That one, no, not that one. Those were water tube boilers. They weren't a fire tube with your typical. They could run really high pressures. It's just a series of tubes in there. First, in the firebox side,
it's not that type of boiler.
It looked kind of like that.
It was a standard D&H 280. They just reboiled it.
Yes.
Reboiled it.
Yep, exactly. Thank you.
And so the steam dome is welded too, it looks like, and you put it there at that time?
Yes, because this would have been very good. Up here, there still would have been a flange on here that was riveted to the barrel. That went away as well. They cut a hole in the boiler course, and there'd still be a flange on it, but the flange would come down and butt all the way around on the shell itself, and they weld that full penetration.
Is the mud ring riveted? I mean, I'm not that.
Yes.
So they did
This
still
particular
have
case-
some rivets.
They've just rivets right here on the mud ring itself. But that would be about the only rivets on the whole structure.
Why didn't they weld that? Why did they use rivets there if they welded the rest of it?
I don't know, that's a good
Okay,
question.
all right, I thought maybe.
Stump the panel.
I'm sorry.
I don't know why they did it that way. You'd think they would just,
Yeah.
Weld in.
It looks like that'd been easier to weld than all them rivets. Yeah.
yep, you would think so, but it was a D&H.
Do
All right.
they rate the welds as efficiency as well, or is that?
Yes, and one of the holdups on welding boilers originally is if you weld this whole boiler together and you heat treat it, post-weld heat treat it, that's all well and good, but you had to take a penalty on all your joints, in particular where the longitudinal seams would be. This probably would have been 2 courses versus, and they just welded the 2 together. If it's riveted, there'd probably be a circumferential joint, well, right in here or right in here, either before or after the steam dome. Run that by me again.
Do they rate the weld
Okay,
for
yes.
efficiency?
So basically, what was required was, and you welded something like this, an unstaged section, you had to have the weld x-rayed. And if the weld was x-rayed and had no flaws, you could call it 100% efficient. If you didn't have the weld x-rayed, you're only allowed 90%. But that's still about 10% higher than a riveted joint. And the beauty of this whole thing is you could actually make a boiler, 2 different boilers, one riveted, one welded, the same exact working pressure, everything, same. And other roads, there were a few other roads were very aggressive. Roads such as the Northern Pacific, the D&H, the C&O, C&NW, and the Milwaukee Road were very interested in using welded boilers once they became acceptable and because of all the reasons we talked about. Few roads, like the New York Central and the CP, purchased 1 or 2 of them just to dip their toe in the water. But the problem was, at that time, steam was on its way out. It was in the late 40s, early 50s. Based on everything I've read, the welded boiler was highly successful. It cut way back on maintenance. A steam locomotive's biggest maintenance item is the boiler. The N&W demonstrated with the J's, and then the last 5 A's, roller bearing rods, all that stuff. You could just run them and run them and run them and run them. The maintenance was on the upper side. But the welded boiler, while the welded firebox and safe ending flues made a difference, certainly made a positive difference in the maintenance costs, the all welded boiler, that made a huge difference. Way less maintenance, still maintenance, but way less than a traditional riveted boiler. It's interesting enough, I have a book on the Northern Pacific, called the Super Steam Era. And the Northern Pacific was the biggest user and trier of welded boilers. They ordered quite a few from Alco to replace their existing boilers on certain engines, including their Northerns, including I think one of their Yellowstones. And the decision was made, like a lot of roads did, all of a sudden overnight, we're going to get rid of these, we're going to go to diesels. And so they put a lot of these boilers, brand new boilers, never used, all welded boilers, kind of on the shelf. And when they got to the point where they had enough diesels, they actually sold, I believe, 8 of them, brand new, never used boilers, to the Washington State Highway Department for culverts for highways. Which is funny, and it's like also depressing. It's like, oh man, brand new welded boiler, okay.
Do tank cars now, old tank.
So basically, to wrap this up, this is the wave of the future, but the future wasn't there anymore. The diesels were obviously proven, coldly efficient, less maintenance. I worked for the railroad for 33 years at Strasburg, steam locomotives. We had 1 diesel. I love steam locomotives. I'm not a big fan of diesels, but I do appreciate their efficiency, and there's so much less maintenance. As I wrote the article in the Arrow, my heart's with the steam locomotive, but my wallet's with the diesel. That's just the way it is. So basically, I think if this would have been developed earlier, but World War II kind of messed some things up in the country. This probably would have come on a lot earlier than that. I still think they would have been done for it, but even with a welded boiler, the diesels, everybody knows. I'm not going to preach to the choir. So basically, these kind of went away. They went away, and there was no turning back. But it was a cool concept, and just again, shame it didn't come out a little earlier. So, any questions? Yes, sir.
So, in the 30s, when the N&W innovated, was that something new and different in any kind of construction? Or were other things like bridges and the like, ships being welded versus riveted?
Well,
did they kind of innovate, or did they pick up on things in other industries?
Like marine boilers.
no, I don't think it, because other industries were very slow to change from riveting because it was tried and true, and it took a while for other industry to go to weld. I mean, I tell you, they were making riveted bridges regularly even 20 years ago, believe it or not, in some places, especially in Europe. But in the U.S., they just were proven and reliable. So I've seen lots of welded bridges. You have like these doubling plates, several doubling plates on, say, on the girder bridge, and you can see all these plates that would have been riveted before, but now they're all welded. So shipbuilding, I mean, like the Liberty ships, they were welded. Previously, a lot of those things were all riveted together, but the Liberty ships, that was a huge thing in the shipbuilding industry, World War II. They made, I mean, how many, thousands of those things, and they're welded. Now, going back to the ICC where they're so cautious, for those of you who are familiar with Liberty ships, they had quite a few of them, especially in the beginning. They're out in the ocean, all of a sudden they break in half. And they break at the weld seams because they weren't properly, not necessarily properly welded, but they weren't properly treated after they were welded. You can't put a whole Liberty ship in a furnace. Well, I don't know any. And so what you would do, you do isolated heat treatment of the seams. You can do that. You can call an outfit in your shop and, hey, I have this seam I welded on a boiler. I'm not going to put it in a furnace. They'll come out and they'll put what's called chiclets on the outside of it. It looks like those things you can get for your car. It looks like beads you put on your seat and you sit in there. It's supposed to make you comfortable. It looks kind of like that, but with a lot of voltage to it. And that will heat up the seam, will insulate around it, heat the seam up for an hour to stress relieve those joints. They didn't do that with the Liberty ships initially, and they found out the hard way, getting pounded, that, gee whiz, we got a problem here. And they break them up. Yes?
Are the new engines they're building, like the in England or the T1, are they welding the boilers then? Or?
Well, I can't speak for Europe. I'm a fan of the U.S. stuff. I mean, some of the stuff in Europe's okay. The T1,
Yeah, they're going all welded.
I think they're all going all welded with that.
Maybe it was the other T1, the originals were as well, I don't know.
The original ones were riveted.
Okay.
Yeah, the
So
one
they
they're
did
doing
make
now,
change.
the new one, I thought you were talking about the new one.
Yeah.
They're all welded on that, and including the frame, including the cylinders,
Yeah.
everything. It's found it's a lot cheaper to do the welded, they basically weld everything up versus the old way with castings. The pattern costs more than the stinking casting does typically. Yes, sir.
Did Roanoke have a furnace big enough to stress relieve their fireboxes? I've not heard.
They must have had, well, no, I'm sorry. That's an excellent question. Let me back up a second. You didn't have to stress relieve your firebox because of the secondary support.
Oh, you did not?
It was just the shell.
Okay.
For the reasons I mentioned before. If your seam cracks in the firebox, it's going to make a bunch of noise, and you're going to take off the roundhouse foreman. If your barrel does that, good night.
Vertically elevated them in that bull riveter.
Yes, they did. Yes, sir.
Somebody had asked why they riveted the mud ring. Is it possible that was so they could replace the firebox more easily? I am aware that when the N&W rebuilt the K's after World War II, they put in new fireboxes.
Yeah, you were at, you know what, Jim, you're absolutely right. That's what it was. I'm getting old. Yes, that's, thank goodness he's here because I have to remember that part. What they typically do, they'd actually put the mud ring on the firebox itself. Once they built out the floor, and they put the mud ring on it there, and then put the whole 9 yards into the firebox, into the shell. get everything where it's supposed to be, and then they rivet the mud ring, already pre-assembled mud, they bolt it up. Typically, every other hole, they put a bolt in,
Yeah.
and then they put it up, and then bolt it to the shell, and then rivet. Thank you.
I've always heard of, what's the stay bolts and how were they installed? What was the purpose of them?
Well, I have an article for Ken, for the Go to the Arrow. He keeps putting it on there upcoming and explains that, but I'll go over that briefly. Let's see, what's a good, okay, this is good enough. All right, and a firebox is actually inside, again, the outside of a boiler is called the shell. And inside the shell is the firebox assembly. Typically at the mud ring, it's about a 4-inch wide mud ring, a water space. And the mud ring, as you go up, the firebox starts going inward while the shell kind of keeps going up this way. So the higher up you go, the wider the water space is. What happens is, water's in there, you make steam, and what's happening is the steam pressure builds up, it's trying to collapse the firebox. It's trying to crush the firebox. And what stay bolts do, and again, roughly averages, every 4 inches horizontally and vertically is again, generally speaking, is what the pitch is, center to center, of one stay bolt to the next stay bolt. And that's a calculation. Because again, the steam pressure is trying to push the shell out and it's trying to crush the firebox. So you want to keep them parallel or where they're supposed to be. So the stay bolts, as the name implies, stays the shell to the firebox. So you do a calculation, you give a 4-inch pitch, that means you go half the distance for this bolt here, you go half the distance here, half the distance to the next one this way, half the distance down here, and half the distance there. So for all 4-inch pitch, that means you have 16 square inches of the boiler, or the end of the firebox, is being supported by one stay bolt. And that's how you figure out how to size the stay bolts, how big a diameter they need to be. And you're allowed 7,500 pounds stress per the rules for a stay bolt, no matter what the material. And the reason for that is, stay bolts break. And if you break a bolt here, that load is going to go around to the adjacent stay bolts. So they knew they were going to break, so that's why they limited the maximum stress on the stay bolt to 7,500 pounds, which gave them factor of safety somewhere around 6 or 7, versus 4 minimum for this portion of the boiler. So that's how you calculate, that's why the stay bolts are there, what they do, and why there's so many of them. Is that making sense?
No. So you actually have to just drill holes, you drill holes and then insert them then? Is that
You have to drill the holes. Typically the holes were drilled before the boiler was assembled. And then you hopefully the engineering was good. When you put the firebox inside the shell, the holes actually line up. Stuff happens. And so then once they're in place, then you run what's called stay bolt taps, varying lengths, real long, with threads, a reamer portion, then it transitions to threads, and you cut the threads with a bolt tap right through the shell into the firebox, and the threads are in time from one sheet to the other. So you don't tick off the machines when he makes bolts for you to put in there,
So,
and the threads aren't in time.
so the firebox is basically a firebox inside the boiler.
Mm-hmm.
Talk a little bit, very briefly, if you will, to wrap up, and tell us a little bit about the crown sheet and boiler explosions. I believe you told me once it wasn't necessarily a flash of steam or
Correct.
or whatever, how that happens.
Yes. Just happen to have a photo of a crown sheet. All right. Crown sheet is the uppermost portion of the firebox inside the shell. And this is the crown sheet right here, going the whole way across. Comes down to here, called the radial area here, and it transitions to the side sheets right about here somewhere. Before I started working on these things many moons ago, I always thought and read that,